Welcome to this very first video in a collection of videos about SANs. In this we're going to take you from beginning to the end on sizing your SAN, understanding the fundamentals, to actually installing a Netapp. In the first few videos we're going to cover mainly theory just to understand what a SAN is and its advantages over local storage. And then as we move through the videos we will get into practical hands-on. So to start with, what is a SAN? Well, a SAN stands for Storage Area Network. And it's a piece of hardware that sits on your network and communicates to your servers to allow a single location for storage. SANs are generally classed as enterprise level hardware. As you'll see from this first set of slides, they have built in a lot of specialist software and redundancy for mission critical kind of application. There are a lot of manufacturers out there, as this slide shows. We've got Dell, which are famous for their for their Equalogics. We have Netapp for their filers, or used to be called toasters. There's some new ones that are coming up on the market, such as Nimble, and you've got your EMCs. Now these vendors will all have their advantages and disadvantages as well as price points, and within their range of SANs they'll have different levels. So this video is predominantly aimed at the SMB market. So that's the kind of 4 to 5 hosts with maybe 30 to 40 guest operating systems in a Wintel environment, typically with a few SQL servers, a few file servers, a couple of Exchange servers maybe, all with different workloads. Typically as we go up into much larger organisations, then they'll go for the higher processing SANs and predominantly blade type servers, but very much when you're going into this field you will have specialist dedicated teams. The reason why I put these videos together is I think it's important as an IT manager to make sure you've got a good solid understanding of your infrastructure. Now, while most companies will still probably want to get outside help in setting up their SAN environment, hopefully these videos will give you a good solid understanding so that you can make sure whoever sets it up, whether it's in-house or external, you're able to make sure you get the best out of your vendors and understand exactly what you want. So here we have a typical demonstration of how a SAN communicates to its environment. Now this slide shows a fibre channel. That's in that the SAN or disk array communicates with the hosts, which could be a hypervisor type host, so a Hyper-V or VMware, or it could connect to what we would call physical servers that have got an operating system stored directly on there. Now up until a few years ago, fibre channel was the way forward, and this typically required knowledge of fibre networking, fibre switches, which are different to typical Ethernet switches, HBAs, and knowledge that wasn't necessarily available to your average SMB. And this made not only the SAN expensive, but the infrastructure required for it prohibitively expensive. Now in the last few years, a new protocol called Iscsi has emerged. So what Iscsi is effectively is it encapsulates the SCSI protocol into a standard IP packet. And most of us will be familiar with SCSI from the local storage. This was before we had SAS and SATA. But the concept's exactly the same, but it's encapsulated in an IP packet and actually uses standard switches and standard Ethernet ports to communicate between the hosts and the disk array. Now, this makes the equipment and knowledge easier to transfer from your standard networking infrastructure into Iscsi. Now, that's not to say that there are some differences and things that we need to be aware of. Like standard networking, we have to understand the kind of bandwidth that's required. We also need to think about segregation of data to make sure that our management and our data for our main network to our client machines is actually overloading the Iscsi network. So throughout this video we're going to concentrate predominantly on Iscsi because it is the cheapest and arguably the easiest protocol to set up. So the standard setup, as we can see here, is we've got a number of host servers here, we've got our switching, and we've got our disk array. What you'll notice is that almost all the hosts will have diverse routes to switches, and then the disk array will have a diverse route to both switches. One of the key things when we set up this storage infrastructure is to make sure we've got resilience. We're putting all our eggs in one basket. So like I said, why would we use a SAN? Is it not too risky? We're putting all our eggs in one basket. That SAN breaks, or that switch that's serving that SAN breaks, and we lose everything. At least when we've got local storage on each of our servers, we lose one server, we lose a collection of guest operating systems. So there has to be a good compelling argument to put a SAN in. So there are advantages over local storage. One of these is administration. It's far easier to get the overall view of your storage infrastructure from one management tool as opposed to having to go onto each individual server and review it individually. When we talk about storage, there's always two main aspects. We've got capacity, i.e. how much storage do we need, but we've also got performance, and these are not mutually exclusive. For instance, we may want huge amounts of data, terabytes. Well, we could quite easily purchase 4 terabyte disks, 2 or 3 4 terabyte disks to serve the amount of storage space we need. However, we also need to consider performance, and we'll get into much more in depth in the next video about performance. But ultimately, a physical disk can only provide so much performance. So often we need to have multiple disks in our disk array to be able to meet the performance requirements. This means that often we may need more disks for performance than we need for storage, or vice versa. And if we are trying to calculate this for lots of different servers, the workloads can change on those servers, and unless we're very specific about what that server does, like it is just an archive server or just a file server or just an exchange server, it's difficult to calculate the loads. So by using a storage array, what we can do is tackle both of these kind of requirements. We can have a large number of disks to handle the performance side of things, but we can also match the capacity of those disks, so our overall capacity requirements will also be met. Enhanced resilience might seem a little bit strange when we're putting all our eggs in one basket, but if you think about it, when we have our local storage, there's only so much resilience we can put in place. If we're putting everything into one single storage array, we can invest money and time into making sure absolutely everything has got redundancy. So we have redundant power supplies, redundant controllers, redundant cache, redundant paths. We can build this redundancy, and we only have to do it once. This way you get much more bang for your buck as such. SANs also have advanced software capabilities, so above and beyond just serving data, they are able to do complex caching, increases the performance. So the caching algorithms can do read ahead, so you access a file, the SAN tries to work out what you're going to do next, so it copies it into cache, and we can put great big pools of cache in one place. So instead of having lots of little bits of pools of cache on individual local servers where sometimes it may be empty and sometimes it might be full, we can pull all that together, put a large amount of cache in there, and we can get the best use out of it. There are two types of cache in SANs. You've got your volatile and non-volatile, and that's for the different type of operations. So when you're writing, a SAN will cache the write into memory in non-volatile memory, and it will send the request back to the server to say that that data has been written even before it's been written to disk. And what it will do is it will build up its cache and then do a sequential write and flush that cache to disk when the disk is at a level that it can accept those writes. So this way the SAN can respond to peak loads by writing to cache and then flushing to disk as and when it can. This has to be non-volatile, because if we suffer a power failure to our SAN, that information that's held in RAM needs to stay there, otherwise we will lose data when the SAN comes back up. We also have volatile cache, and this is for the reading side. So as I said, information that's read up can be held in cache in case it's going to be reread by another server, or in some cases the algorithms can read ahead and predict what it is likely that you will be wanting next. This can be cheaper RAM, because if the SAN crashes or needs to be rebooted, it doesn't matter that information is lost because it's already on disk, and we can enter it into cache when it's accessed again. In addition to this, the software can do high performance stuff like deduplication, which reduces the amount of data that's physically stored on disk. Because the array has all the data for all our servers, we get much more efficient deduplication. and we'll cover this later. And we get lots of management tools such as snapshotting, replication and thin provisioning, again something we'll cover later, but meaning we don't need to carve up all our storage for our host machines in advance. We can allocate space almost on demand. So yes, it is riskier by putting everything into one place, but we can build enough safeguards around this that risk is certainly outweighed by all the great advantages we get. So here's a demonstration of a particular problem we have when we've got physical machines and we're storing everything locally. When we're sizing our servers, we have to take into account peak loads. Now, for email servers, typically first thing in the morning, 9 o'clock, everyone turns up, your Exchange server gets hammered as everyone's downloading their emails from the night before, and then throughout the day it plateaus off. SQL Server, it could be sitting idle for 80% of the day, and then you have a department that runs a lot of high intensity reports, and you've suddenly got peak performance. So the problem is we have to size these individual machines to take account the peak performance, the peak requirements. And therefore quite often we've got disks sitting there doing nothing for 20, 30, 40% of the day. And then we are having to invest a lot of time and money to make sure that the server can serve the requests when that peak requirement does come. And as we scale this out over to many servers and we look at those workloads throughout the day, we'll see that quite often the CPU is very spike and then idle for a few minutes, then spike. So the idea is if we can move all of that into a single location, then instead of having to have our systems sitting idle for 20 or 30% of the time, we can take those diverse workloads, and as long as we size our SAN correctly, we can get much more from less disks, because they are taking into account that sometimes one load is quiet and another load is peak. Now obviously if we've got 20 servers that have all got constant 100% peak loads, putting that onto a single SAN makes no sense at all. So when we're starting to look at sizing our SAN, we need to make sure that we fully understand our workloads and what our peak and idle times are and what our overall performance requirements will be. We can see this demonstration here. We've got 2 disks that are sitting idle, and then later on in the day we've got another 2 disks that are sitting idle, and then at some point we've got 4 disks that are sitting idle. What we can do is bring these all together, and actually we could reduce our number of disks by 2. Or, indeed, we could keep those disks and utilise them for something else. So this is the back of a standard Netapp, and what I want to show you is the resilience that's built in. So we look here, we have dual power supply. In the event of a single power supply failure, the other power supply can run the whole system. Now they're shown in orange. Orange means it's hot swappable. So this means even in the event we do have a power failure, we can simply pull out the old one and get a replacement one from Netapp if you've got the right support within 4 hours, and pop that power supply back in. And okay, so you're running risky for 4 hours potentially, but hopefully dual failure is highly unlikely. This isn't unique to Netapp, this is standard. Even within servers we run dual power supplies, but all SAN technologies will have dual power supply. And then the second type of resilience is dual controller. Now we're going to talk about the different types of dual controller later, but we have active and passive and the different types of controllers that are available, and we will go into that in more detail. But ultimately the controller is the brains of the system. It's what's processing the requests and requesting the information from the physical disks, handling the caching. It's where all the RAM is stored. So we have dual controller means that in the event of one failing, the other one can take over and serve those requests. So we have a very high level of redundancy. In terms of the disks themselves, we will use traditionally RAID 6, or in the Netapp RAID DP, which is a type of RAID 6. And this will give you redundancy in the event of 2 disk failures. You will also set up hot spares, and most advanced SANs, what they will do is they will look for predictive failure, and this is as soon as a disk shows any kind of corruption at all, before it fails, it will actually copy the information from that disk onto a hot spare first. It is far faster to copy the information from a disk that is in the process of failing than to have to rebuild a disk from a RAID parity. And what typically the Netapp will do is copy that information to a hot spare, and then it will put that disk that he thinks is failing into a maintenance mode, and it will carry out lots of different checks on it. And if it thinks it is going to fail, it will flag this disk as failed, and we will swap that out with a new disk, again generally within 4 hours, and that new disk will then become the active hot spare. And then not only do we have dual controller, on each controller we have dual network as well. Now this will help us when we're looking at the whole topology about having multiple switches and multiple paths, so that we can handle NIC failures on the SAN or switch failures or a NIC failure on the server itself. So as we spoke about before, there's dual controller, and there's two types of dual controller. There's active-active and active-passive. Active-passive is really simple. Basically you have one controller that handles all the load and one controller that's identical that sits there idle until the first controller crashes or has a fault, and the second controller takes over and handles 100% of the load. This makes sizing really easy because you know in the event of a failure, your other controller will be able to handle the load exactly the same, and as provided your first one had no performance issues, your takeover one will have no issues either. The disadvantage of this, of course, is you've got all this expensive cache and processing power sitting there doing nothing. Now the other type of dual controller is active-active load, and in active-active load both processors are active and both of them are serving data. Now the advantage here, of course, is that you're getting as much bang for your buck in that you're getting double the amount of cache and double the amount of processing. The problem being is that in the event of a failure of one of the controllers, the second controller will take over the duties of the first one. Now the problem is if the first controller has been operating at 100% and the second controller is operating at 100%, in the event of it having to take over control, the controller obviously can't handle 200%, and as such will introduce latency issues and processor issues. Now the two main parts of this is really CPU and bandwidth. As we'll see later, bandwidth really isn't an issue on SANs. The disks will always be far slower than what the bandwidth is available. So the main thing is really to look at CPU. And this is something in an active-active system you'll have to monitor, because the trends of CPU are different throughout the day. For example, during normal operation the CPU may be quite low, but in the evening when it's doing one of its fancy tasks such as deduping, it will be running at 80 or 90%. So actually having an active-active can be quite beneficial because you are being able to use your processors effectively during the day, and then in the evening you can ramp both processors up to 100% to do the deduping. Now the event of a failure, it's not a big issue if you pause that deduping in the evening, because it's not going to make a big difference to your environment. So the fact that you do need more CPU for that process won't be affected if you're in an active failover. And likewise, you'll only be in this situation for approximately 4 hours while a new controller is being shipped to you and you install it. So the question is, having slightly reduced performance for 4 hours as a disadvantage, along with having two controllers that have been able to work fully and serve the data and getting the advantage of using all that quality processing equipment, it's a tricky one and people have different opinions. Personally, I loathe equipment sitting there doing nothing. It's just not right. So I quite like the active-active setup, but it puts management's responsibilities to keep an eye on the CPU load and to make sure that we're not running both. Now in an active-active load the disks are evenly split, so it's not like you're going to have major IOP problems or anything like that when you go into a failover, because the disks will follow you to that controller, so you'll still be using the same amount of disks. It's just the CPU that will take that extra hit. Other advantage of using a SAN. Most people know of VMware or Hyper-V as a virtualization solution. It's great because it allows you to sweat the assets of the server in the same way as we spoke earlier about the SAN and loads. We have exactly the same thing with servers in terms of memory and CPU, in that for a lot of the time they may be sitting idle and at other times the loads will be really high. We can put all of these guests onto a powerful server and make sure that the server is running 80–90% of its load the whole time, and we're getting the most out of our hardware. In the event of a failure on the host, if we're using shared storage, another host can take over the responsibility of serving those VMs because it has access to the physical disks that those guests are stored on. Of course, there's many more questions here about making sure you've got enough capacity on the host to be able to take that over. But also we have things like resource scheduling. So you can quite often have DRS where the servers, you have more physical hosts, and then the VMs will be moved around depending on workload. Indeed, even in the evening, you can shut down entire host servers to save energy if you can put those VMs onto other servers that are not being used as much during the night. All of this requires shared storage, so it's vital that we have a SAN, and this is just another good advantage. So we've spoken about the redundancy in terms of what the Netapp or the SAN itself has. Now we talk about paths. In here we've got a standard SAN setup here. We've got two switches and we've got a host. And the idea of this slide is to show about the concept of multipathing. The idea is that in the event of a particular failed system, we can still get data from the SAN to the host. And each route that the host takes to get to the data is known as a path. And therefore, we talk about multipathing. So I'm going to take you through a slide here that will show you each different component failing and how the data will continue to be served. So in the event of this controller failing here, we can see that data can still be got to the host by this controller that will have taken over responsibility, which we saw in the last slide, for serving the data. We can see the data can come from here, down the host, and up here. So in fact, actually, it's still got dual path. And likewise, if this controller fails, this one will take over, and again, we have dual paths back to the host. Now, what happens if one of these switches fails? Well, that's fine because each controller has a path to each switch, and each switch has a path to the host. So now we're operating on a reduced system because this path is no longer valid, but the host can still get to the SAN. Likewise, this switch fails, well, the same thing. The SAN can talk to the switch, and then the switch still has at least one path back to the host. We have a NIC failure, or someone's unplugged the network port off this particular path here, where we can still see that we have access to both controllers. And likewise, the other NIC fails, we can now see that we've got access via this switch to both the controllers. So provided our usage doesn't exceed 50% of the bandwidth available, in the event of one of these failures, we'd actually see no performance degradation at all. And this is a standard setup in an iSCSI environment. Now, I spoke earlier about one of the advanced software features called deduping. And to give you an understanding of how deduping works, if we have a server and it's running Windows 2008 R2 as its base operating system, we all know that that install will take 30 gig of memory. We have another server sitting as another guest on the same host, and it's another install of Windows 2008 R2. We have two pretty much identical copies of an operating system that's taking up 30 gig and another 30 gigs, so that's 60 gig of data that's been used, where a lot of these files are the same. Now, of course, the server will have additional software applications, and there'll be files within the Windows 32, the Windows and the System 32 folders that are not the same, but there's going to be a large proportion of files that are, including things like Windows updates. You install Service Pack 1, that's an extra gig across two servers. What deduplication does is it has a file on server 1 and a file on server 2. Because both these servers have got these files stored on the same SAN, the SAN has the overall view of everything. So the C drive of server 1 and the C drive of server 2 are both stored in a data store called Windows servers. And there's one of thousands of files, as a demonstration here, that's 100 meg big. What the SAN does is it will scan at regular intervals, normally out of hours, and look for files that are identical. And in the event it finds an identical file, what it will do is it will replace all the additional instances of that file with pointers. So when a request comes in for that file, it'll go to the pointer and then be directed to the physical file. And this can have significant savings, certainly when you put all your OS drives onto the same data store. And we'll talk about this later when it comes to design. Likewise, there's other places where you'd have a lot of replication of data. If you are backing up, say, a SQL database, and you put that on a data store, and you take a backup today, and then a backup tomorrow, and then a backup the day after, a large proportion of that database is going to be identical. Obviously, there'll be some changes. But the idea of deduplication is it will actually say, well, in 5 instances of that backup, 80% of that data is the same, so immediately you get an 80% saving on those duplicated files. And this is all handled behind the scenes. You don't see anything, but what you do see is a statistic saying how much of the space has been saved. Likewise, if you've got a large file server that's got hundreds of Word files, even things such as having your company logo on all those files, that's going to be the same bits of data within a file. So the key here is, although I said earlier it was looking at the whole file, it actually is looking at the individual bytes, and it will match bytes and put the pointers there. So even if you've got 2 Word files that have got a 25k image embedded into them, although the rest of the file may be different, that part of the binary stream where it is the same will also get savings through deduplication. One word of warning is salespeople will push this heavily and tell you can have 50% savings, and they'll try and get the overall cost of the SAN down by saying, well, actually you think you need a 500 gig, you only need 250 gig because there's a 50% saving. I'd be very wary of this and always try and size appropriately. And if you really are getting pushed and need to cut down amounts of space, I would suggest that you actually ask for a loaner unit to actually test the kind of levels of deduplication you'll get. And this brings me to the final slide of this introductory to SANs. We've looked at a lot of advantages, and a lot of them are quite scientific and easy for me to describe. I call this the magic part, and this is because it's not really an exact science, and therefore there can be quite a big gulf between what the sales people tell you, what the SAN vendors publish on the web, and what we get in real life. However, there is some significant advantages in performance in using a SAN above and beyond local storage. Every single physical hard disk, including solid state, but I'm predominantly talking about SAS drives, will have a performance. That will be how many IOPs it can serve and what its latency is. And you would expect that if you put 2 hard disks together, you'll get double the IOPs with the same latency, or you could have the same number of IOPs with half the latency, and I'll explain all this in the next video. What the magic does with using RAM and caching is to take those hard figures and increase overall performance. This is great, but it's very difficult to calculate when sizing your SAN, because it's very dependent on the kind of workloads, what you're doing at the time, the amount of data, etc. So I personally recommend sizing your SAN to what would be required without the magic. But what is the magic? Well, data comes in. As it comes in, it hits the RAM and it's stored in the RAM. When the workload is significantly reduced on the disks beneath, or the RAM becomes saturated, i.e. full, it will then commit that data to disk. This, as we all know, RAM is infinitely faster than physical disks. This is great because the operating system is getting a confirmation of the write of data in fractions of a second. So provided our RAM can flush to disk fast enough than the RAM becoming full, we'll see a good performance advantage. The additional advantage, and certainly in some SANs, is that sequential writing of data is far faster than random writing of data. So by filling up the buffer in the RAM, we can get sequential bytes, and then this can be flushed in one go. So in terms of writing, the RAM really does make a significant difference. My experience in storage shows that the latency within writing is always minimal. It really does make a big difference. And if you actually are starting to see high latency in writing, then there's something seriously wrong in the design or in the infrastructure. Reading's somewhat different. When the server and user requests a piece of data, it will come through the RAM and it will check to see whether that piece of data is already held in the RAM. If it's not, it will have to go to disk and read from disk. On the way back out, it will copy it to RAM as it serves it to the individual host machine. There's two advantages here. If another host or the same host comes back and requests that data again for some reason, it's already sitting in RAM and can be served much faster. Furthermore, the algorithms, and this is the magic that I talk about, can predict what you may be coming to read next. So if you are paging a table out of a database and you request a page, it will read that from the disk, write it into RAM. It's highly possible that the algorithms in the SAN technology will understand that it's a SQL table and possibly be able to read the next page into RAM before it's required. And it's the magic or the code that is written to understand what the predictive read is that will vary between SANs, and you'll hear the salespeople saying, "Oh, well, ours is the best technology and it can be more predictive, and that's how we get stuff into RAM." There's a couple of issues here. Firstly, RAM is not infinite, so if you are absolutely saturating that RAM, every time you read, it can't be cached into RAM, or as it is cached into RAM, stuff that hasn't been accessed is marked as dirty and gets pushed out of RAM. So when the request comes in for it, it'll have to be read from disk. So that said, it's very difficult to work the predictive loads in terms of what the RAM and how much RAM it can give advantage. Now, when we're actually running performance stats, certainly in Netapp, we can see what the cache hit rate is. And what that's effectively telling us is how much of the requested data is actually coming from RAM and how much is having to come from the disks. And this will give us a good indication of whether we've got enough RAM. Of course, when sizing your SAN, the sales and pre-sales engineers will be able to give you an indication of how much RAM you need. And of course, the RAM comes down in price. We see that the filers, the SANs, have more and more RAM. And what's happening more and more now is where solid state is still too expensive to use as your main storage, we're using it as a kind of bigger RAM because it's cheaper than having gigs and gigs of volatile RAM, and almost using it as a permanent caching state. And certain SANs, such as Nimble, are doing this very effectively, and they can have some amazing IOPs and latency rates. Some of the other vendors, the Netapp, are a little bit further behind, and of course it's a licensed feature. Eventually I assume we'll see more and more solid state being used as the primary storage, and we'll be what we call tiering the data. So your solid state is where your SQL databases and your Exchange databases will be, and your file server stuff is on your second tier, and your backups are on SATA disks. And the filers will become intelligent, and they'll understand by looking at the packet analysis of what you're doing and actually store the data in the right place. And this is already happening, and this is again the magic, what makes better use of those physical resources. I'm James Sillett, and I'd like to thank you for taking the time to watch this video. If you have any comments or questions, you can contact me by any of the means shown below.